Hello everyone and welcome back to the channel. About an hour ago, Donald Trump raised a bunch of tariffs against all imported goods in the US, which got me thinking about why don't I raise the prices of all of the foot pictures that I put out on OnlyFans. Right now I'm giving them away. No, like I'm literally giving them away. I keep trying to give them to people and no one wants them, so I guess maybe I shouldn't raise those prices. But anyway, let's go ahead and talk about distributed systems. Today we'll be talking about Google Zanzibar. Okay, so as I mentioned, today we're going to be talking about Zanzibar, which is a paper out of Google in 2019. So basically, Zanzibar is a paper or a system that's responsible for managing Google's ACL lists, so their access control lists. And the ACL problem, although you can think about it from a security perspective, because that's really what this is about, it's right, what users can access what content, really it can be modeled as a graph problem, right? Because even though in its simplest form, it's really, does user X have permission to object Y, there's actually some complex relationships when it comes to permissions, and that has to do with things like permission inheritance and, nested permissions and things like that. So for example, if we were talking about something like a Google Doc, for example, we've got document X over here, and document X can be a part of a folder Y, which could even be a part of a folder Z. And a user that has permissions for folder Z actually has permissions for document X by virtue of having permissions for that parent folder. And also sometimes you actually end up getting basically different roles, right? So you might have an owner role where an owner might have editor and viewer permissions, and maybe that editor role also has viewer permissions. So ultimately this results in a surprisingly complex problem that has to be solved fairly quickly. The reason it has to be solved fairly quickly is because ACL checks are in the critical path of every service, right? Like when I'm loading a document, first I have to be sure that I have permissions for it. And this is especially true for things like an internal search engine, right? If you're searching across a bunch of documents, I only need to be shown documents that I have permissions for, otherwise I shouldn't be shown those results. Now note that in theory this entire thing could be denormalized, right? Like I could, if Edward Snowden has permission for document X, maybe there could be an arrow directly there. But denormalizing this type of thing means that if for whatever reason Edward Snowden, were to be removed from folder Z or something, now I have to remove all of these arrows that go from Edward Snowden to folder Y and document X. And so ultimately that doesn't really make very much sense. So this is why we model it as a graph. Ultimately we have to do things kind of like traversals, and we'll kind of get into how we speed those up in a little bit. So basically when it comes to a system like an ACL system, the real problem that Google says they want to prevent is something they dub to be the new enemy problem. So basically the idea is if I had permissions for something and then I get removed from that object and then someone makes a change to that object, I shouldn't be able to go ahead and see it if I made a stale read about my own permissions. So the example that I chose to use here is obviously I was dating Corinna Koff. That's no longer the case. I have a new girlfriend. So she breaks up with me right over here, and she says, "You're no longer on my Snapchat story, Jordan. You don't get those privileges anymore." Then she adds a new Snapchat story talking shit about me. And then finally, I proceed to click her Snapchat story, which I apparently still have permissions for because maybe I read from some stale replica that says, "Jordan, you still have permissions for this thing," even though, she removed them 30 seconds ago. I see the story, I get mad at her, and then we fight. So I guess ultimately the point is we want to prevent this type of thing, right? It shouldn't be the case that when someone makes a change to content, I can now go ahead and see those contents that should be guarded with me. It's the same idea of like removing someone from a group chat, talking about them, and then they can still see the group chat. You don't want that happening. So the question becomes, well, how do we actually solve this? When it comes to making reads that aren't stale, traditionally we've had a few options. Number one is you just read the current state of the database. Now, if we're talking, like a multi-leader, leaderless database, that means we need to coordinate across those leader instances, right? If we have multiple leaders, we need to basically converge their state somehow and read from that. Same goes with leaderless. Maybe we would need to read from a quorum of nodes, and all of those things are going to be very expensive. Probably involves us reading from multiple different data centers at once, which is inherently going to be expensive, which, like I said, is bad because all of these reads are in the critical path of our services. Another option that we see far more frequently is just reading from a leader database, right? So if we're using a single leader setup where we have one database that's a leader and multiple follower databases, we just go ahead and read from the leader, and now we have an up-to-date read, and we know that we're not going to read any stale data. So that one does work, which is great. But at the end of the day, Zanzibar is a global service. And so if I'm not in the data center, or at least close to it, that the leader database is located in, now all of a sudden I'm going to have a slow read, and the service is going to decrease in its speed very quickly, and those reads are going to be higher latency. And in addition, another problem with that is just availability, right? Like when a leader goes down, we have to perform a failover, and that can take a few different, a few seconds or something like that, where no one's able to make any reads. So ideally, we're not going to be, needing to rely on reading from a single leader. Ideally, we should be able to read from local replicas as well, because if we can't, now all of our reads have to go across multiple different data centers, and that's when you really start incurring higher latency reads. So basically, the main kind of concept that Zanzibar employs here to make their system fast while also correct and avoiding the new enemy problem is basically, I don't actually have to read the authentication state in its current form. I just have to read it in its form that's definitely after the last time I modified content. So for example, if Corinna Kopf, makes some new Snapchat story post and doesn't want me to see it, as long as I read the authentication state anytime after that post was created, then I know I'm good to go. I'm not going to be able to see her post. I'm not going to get mad at her. So another thing about that is that means that because this state of the post, maybe a few minutes back or a few hours back, there's a good chance I don't actually have to go to a master database node to read it. I may be able to read it from one of my local replicas, because replicas are getting data asynchronously, and as a result of that, you never know when they're going to be updated, but hopefully they're going to be updated enough that we can make a read locally and have it be low latency. So in practice, basically, what they find in Google is that these quote-unquote safe reads, where safe reads are ones that can be served from their local data center, are done 100 more times than the ones that require us to go to the master node itself, where you really only have to go to the master node when you need the freshest possible copy of data. Another thing worth noting about all of this is you notice that I said, I'm making a read of the ACL state after the content change, right? So Corinna Kopf makes a content post, and then I have to read what the data looks like after that. That implies that all of our writes need to be ordered. More importantly, globally ordered, right? I need an ordering between when Corinna Kopf actually, adds that Snapchat post and when I read, the ACL data. So even if these are two fundamentally different databases where that content is stored and where I'm reading the ACLs from, I still have to make sure that I'm reading from a snapshot that would be after that conceptually, which means we kind of need this concept of external consistency, where this is a little bit different than linearizability, because linearizability means that every single write in a database system is totally ordered, which is valid, but they can be logically ordered, right? Like I can assign a monotonically increasing number to every single write and put them in a log. Externally consistent basically means that these writes are consistent across all systems and all databases. And what better thing to provide external consistency than a timestamp? As we know, timestamps in distributed systems are kind of shaky at best, and so what we're going to be using instead is Google's Spanner. So we've spoken about this one in detail, and I'd recommend watching the full video there, but the idea here is that Spanner is a system that provides external consistency by virtue of using timestamps, and basically the main invariant that they want to provide is the following. If I have two writes, a write A and then a write B that can only be written because the user that wrote it first read write A, meaning that B is causally dependent on write A, I know that the timestamp of B that is provided is going to be greater than the timestamp of A. So the timestamps themselves may not be completely perfect, but the point is that causal relationships are maintained in the timestamps that are provided to each write, therefore effectively making this entire thing externally consistent. As long as the timestamps are provided by the same system, which they are, they're all provided by Spanner's TrueTime API. So just as a quick refresher, how do we actually go ahead and maintain this invariant? Well, the idea here basically is that, if I have two writes, A and B, and they go to their local computer and say, what time is it? Even if B comes after A, B might actually have a lower timestamp assigned to it at first. That being said, Spanner's TrueTime API effectively gives a bound where we know the actual time is going to be in that bound. So we know that if basically A happens, and then in Spanner, before we actually commit A, we take basically the delta of time between A min, A max, we wait that amount of time, and then we commit the write. So now we know basically that the actual commit time of A is whatever the assigned time of A was plus A delta. And we know that that's going to be greater than A max because we've added this A delta amount. What that basically means as well is that whatever this time is here, we know that because of how true time works, we're being assigned valid bounds to our timestamp. B is going to get assigned a timestamp at the computer. Maybe it's even before A to start. But we've got B min, and then we've got B max. We know that B max has to be greater than this A local plus A delta because of the fact that B actually happened after that point, because we waited until this point to commit A. And since B literally happened after that time, we know B max at least has to be greater than it. So then the timestamp that we end up assigning B is B local, whatever its local computer assigned it, plus B delta, which is B min to B max. And then the idea there is basically, since that value is going to like hopscotch us to this point over here, which is greater than B max, we know that the timestamp of B is going to be greater than the timestamp of A. Not overly important. The idea is just that this invariant holds, and you can think about it like that. But, Spanner is done effectively using that to provide timestamps, and then it's going to create a distributed log via Paxos, right? So in Paxos, we've got a master, we've got a bunch of replicas. The master is always going to be able to serve reads that are up to date by virtue of using a master lease. That being said, the replicas, which can be stale because, the master commits first and then sends entries over to the replica, has a certain number of log entries on it, and it knows which timestamp it can serve data up to. And so if we only care about the state of an ACL list, maybe this guy has 10, 11, and 12, and we care about the state of an ACL list at time 10, oh great, we can actually read from our local replica. So that's going to be very useful for us. So the way that this is kind of all facilitated is through this concept of a Zookie, which I don't really like that they use this word because I think it complicates things, but the idea basically is that a Zookie is effectively a spanner write timestamp, right? So basically, if I am reading from Zanzibar and I provide it a Zookie with timestamp t equals 10, I know that the data that I then proceed to read back from Zanzibar will include all writes at least up to t equals 10 and possibly some even greater than them. So as a quick example, basically here's how we're going to enforce ACL checks in Zanzibar. If I'm Corinna Kopf and I want to remove me from her Snap story before making a new post, at t equals 1, basically she's going to remove me from the access control list, right? Then the next thing that she's going to do is go to Zanzibar and say, all right, I just made a change to the ACL list, and now I'm going to make a content change. So now I'm going to do this content change operation, and Zanzibar is going to return me a Zookie if I'm Corinna Kopf. So the Zookie, since we know it's after t equals 1, because that was before this, we just removed me. Let's say this is at t equals 2, the Zookie has t equals 2. Now when Corinna Kopf goes and creates her Snap story, that t equals 2 Zookie, she's going to store in the database. So regardless of what database she actually uses, regardless of where Snap stories are posted, she'll store that t equals 2 alongside the post metadata. And then finally, when I'm going to look at Snap stories and reading that database, I'll see, oh, okay, here's a t equals 2 Zookie associated with this. So let me read the database permission, or the Snap story post permissions at time t equals 2. So I'll go back to Zanzibar. I'll say, hey, show me the state of the world as of time t equals 2, and this guarantees that I'm going to see this change from t equals 1. I will see all writes up and including until time t equals 2, and possibly more than that as well. I just know that everything's going to be correct. There's no way I'm going to miss that t equals 1 write. Okay, so quick, aside to just talk about how Spanner is organized within the Zanzibar system, and then we'll go ahead and do a high-level architecture of the entire system. But basically, it's sharded, of course, just has to be. This is a gigantic system. We store trillions of rows. And then ideally, we want to store by the object ID. So an example of an object would be like a document that users can have permissions for. Then there are a variety of relationships that get predefined per client. So for example, if we're talking about Google Docs, they may define the viewer, the editor, and the owner relationships. So you predefine those. They're just strings. It's fine. User IDs, so for example, user Jordan can be a viewer of a document, and then also the timestamp of that change. The reason being that because we're performing this snapshot isolation in Spanner, we need to basically store multiple times worth of data. so that, we can go back in time and potentially, show reads at a particular snapshot. Cool. So basically the idea here is that, this is going to allow us to quickly get all the relationships for one particular object. So all of the people who have viewing permissions for one particular Google Doc. And also it can even work with multiple different types of relationships. Cool. In addition to kind of that ACL tuple table, there's also this changelog table, where the changelog is basically just effectively a log of every single change that goes into the ACL list, round robin to a variety of shards. We'll talk about why this is useful later in more detail, but basically the idea is, occasionally you want to build secondary indexes, right? Because this data is very normalized, and we're effectively doing graph traversals. So in order to speed that up, maybe it would be better to denormalize it so that we don't have to do so many network hops across nodes. Cool. And then the final piece of this is, as we said before, Spanner is kind of a Paxos-based system. So in Paxos, you can have a bunch of voting replicas, which are the ones actually performing consensus, but then you can also have a bunch of read-only replicas that aren't doing any voting. And the reason this is nice is because you can put those in a variety of different data centers. They're not actually hindering the speed at which Paxos can kind of continue to accept new writes, but they can speed up new reads from those data centers because they may be able to serve local reads at an appropriate staleness bound. All right, so let's talk about the high-level architecture of this system a little bit. So basically, of course, we have our Zanzibar servers. Now note that I have this pretty crudely drawn consistent hashing thing here. Basically, the idea is, and we'll talk about this in a little bit, that all of these guys are doing caching in memory, and they're doing so according to consistent hashing on the object ID. So for example, if you've got a bunch of Google Docs documents, based on the document ID, that will determine which Zanzibar server you want to read from. Then, of course, you've also got these spanner guys over here. So we've got a bunch of different regions. Maybe these are the voting replicas. We've also got some non-voting replicas, like I mentioned. It's good to have at least 2 per data center because we'll do something called request hedging, which we've spoken about on this channel before, but I'll talk about it a bit more later. And then finally, we've also got this changelog table. Now, of course, this would be sharded and replicated as well, and it's also in Spanner. So, there should be a quorum there as well. But the idea is that basically from the changelog, we've got this Zanzibar server called a watch server. And the watch server is responsible for basically taking entries to the changelog and passing it to this secondary system called Leopard, which is going to allow us to speed up some of these, very deeply nested graph problems a little bit more by denormalizing the data. Cool. So let's go ahead and talk about Zanzibar in more depth. Basically, not every single read that we do when we go to Zanzibar requires specifying a snapshot timestamp to do it from. Certain times you're just making a read in general, and you don't really have any guarantees that need to be solved. For example, if I'm just going to a search index or something, or I don't know. I'm trying to think of a good example here, I guess just reading from a document where there haven't been any changes at all recently. The idea is if Zanzibar doesn't know exactly what snapshot to execute the read at, it can basically choose one for you. And if it can choose one for you, it wants to choose one that's going to keep the latency low. So if it says, I want you to read from too recent a snapshot, then maybe you won't be able to do a read from your local replica. Maybe you'd have to go to the master. So basically, every single Zanzibar server is constantly keeping track of, kind of how up-to-date local replicas are so that they can basically configure this default staleness so that you're still making reads from the local replica. That being said, they don't want to be too conservative with it, right? Like if you're reading too stale of data, you're definitely going to hit your local replica, but then you're going to be reading pretty stale data. So ideally, they're trying to kind of create a happy medium where the data you're reading is not that stale, but it's still being served from your local replica. This is an annoying bug right here that I can only get rid of by going like this, I think. Oh, nope. All right, there we go. Ha. All right, let's go ahead and talk about metadata for ACLs. So like I mentioned, every single client, so for example, Google Docs, Google Drive, Maps, anything like that, is going to provide a pre-configured list of relationships between users and objects. And those relationships themselves can have hierarchical relationships, like how, an owner is also a viewer and an owner is also an editor and things like that. So that's considered this concept of ACL metadata. Now keep in mind that this ACL metadata is being queried very frequently because you have to understand how ACL metadata works in order to evaluate ACL lists from the lists of tuples. So in order to speed that up, every single Zanzibar server is going to basically cache that ACL metadata that they're responsible for. That being said, when ACL metadata is changed, if one of the Zanzibar servers is updating their cache before the other, now they're on inconsistent metadata versions, and that's going to be problematic, right? If you evaluated the same query at 2 different Zanzibar servers, you may actually get different results if there is a metadata change. And so ultimately what we want to do is ensure that they're all using the same version of it. Basically, there's a central monitoring system that keeps track of the version of metadata on all of these Zanzibar servers, and then basically performs snapshot reads of it at one agreed upon version where basically all of the Zanzibar servers have access to those reads. So as they continue to update their cache, then that central monitoring service bumps the metadata version that everyone will use, and then they'll evaluate ACL checks at that metadata version. Okay, this is really the meat of the video right here, so let's go ahead and get into it. Like we mentioned, Zanzibar's got to be low latency, it's at huge scale. How can we speed it up? Well, there's basically 5 things that it does at a high level that we're going to talk about in more depth. Number 1 is taking advantage of parallelism. Number 2 is secondary indexing. Number 3 is mitigating hotspots through caching. Number 4 is performing throttling of mischievous or badly written clients. And number 5 is going to be doing this thing called request hedging to get rid of tail latencies from external systems. Cool. So the first thing is just going to be parallelism. Like we mentioned, because there are these complicated ACL relationships, you have all of these Boolean trees where there's a lot of OR statements between them. So one example is, okay, can I view this document? Well, yes, I can if I'm a viewer, or I'm an editor, or I'm an owner. So all of these things can be evaluated independently of one another, and they're probably going to be evaluated on different shards of spanner instances as well. So what you can do is basically make all of these API calls in parallel, get the results back, and that's going to speed things up as opposed to doing them serially or sequentially. That being said, you don't want to waste resources, so when one of those API calls returns, if your expression is complete, maybe it becomes very apparent early on that I am an owner of the document, so that API call completes, then we want to cancel the other 2 outgoing ones. Another system that we've added in Zanzibar is called Leopard. So basically, Leopard is going to help us denormalize the data that we have as a result of these graph relationships. So one thing that is fairly problematic that makes kind of dealing with this data hard is all of these nested relationships, right? So in the intro slide, I drew there's a document X over here. That's part of a folder A, and then there's also folder A/B. So really it goes, document X is part of folder A/B because its full path is A/B/X. And then we've also got folder A. So if we kept this data normalized, we would have some arrow from folder A to folder A/B to document X. And then, we would have to evaluate any connections to all of these different nodes. Now keep in mind that the way that we sharded our spanner tables was based on object ID, meaning that something like this guy and this guy are on completely different nodes. Right? So if we wanted to go ahead and traverse all of these nested directories, we're basically jumping from spanner node to spanner node each time and making tons of extra network calls. Instead, what Leopard will do is it won't take out all of the denormalization, but at least for the relationships between objects that are related to one another, like folders, it'll basically denormalize those such that every single related object will have a direct edge to the one that we care about. So for example, document X will have an arrow from directly to folder A/B and also directly to folder A because they're going to be edges on folder A that we care about. So what this allows us to do is basically figure out all of the connected nodes that we care about at once, and then in parallel we can evaluate who has who has permissions for folder A and who has permissions to folder AB. If we didn't do this, these would all have to be serial requests, right? Because first we would have to jump to the node that holds folder AB, then we would have to jump to the node that holds folder A, and only then could we evaluate who has permissions for folder A. Now we can do it in parallel, which speeds us up a bit. Now it's worth noting that we're basically doing the sharding by the object/group in this case, and we're denormalized, right? So if this is one shard right here in this dotted line, maybe we have another shard right here where we have a copy of folder A/B, and then an arrow to folder A. Because this is denormalized, it means we have a lot of copies of data. So this is going to be shard 1. This is going to be shard 2. And then any, instant relationships to these guys, user A or user 1, user 2, user 3. I used 1 and 2 before, so let's say user 10, user 11, user 3, blah, 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 and so on. Okay, so the question is, how does data actually get into Leopard in the first place? We touched upon this earlier, but the idea is through this concept of watches in Zanzibar. Now, watches is basically what it sounds like from Zookeeper as well, which is every time there's some changes via the changelog database, you're subscribing to them and performing change data capture. So the way that we do that is pretty simple. Basically, if I'm a Zanzibar watch server, remember, that's reading from the changelog DB. All I'm doing if I'm Leopard is I'm providing a Zookie with a certain timestamp. So then Zanzibar is going to basically return me all of the entries that have come including and after that timestamp. So in this case, it'll say, ooh, I see log entries 10, 11, and 12. And then Leopard is now going to say, okay, well, if you've returned me entries through 12, now I'm going to provide you another heartbeat Zookie now that I've processed all of those, this time at 13. And if there are entries that correspond to these, it'll pass them back. So maybe it'll be 13, 14, 15. And then it'll continue this process of passing all of these Zookies. This is good because it means that if for whatever reason any of the servers go down, as long as you have the Zookie from before, the heartbeat Zookie, you can continue reading where you left off. Cool. One more thing to note is that in particular, Leopard doing basically these streaming reads from Zanzibar are not completely stateless. They are stateful because, if you're maintaining, let's say you've got some sort of group relationship like this, you've got document ABC, A/B/C, which is in folder A/B, which is in another folder A. When we denormalize this, we get rid of this over here, and we have an arrow from folder A directly to document A/B/C. Now, in the event, basically, that some existing parent folder were to be added to folder A, maybe there's folder A now becomes a part of folder 0. We need to basically be able to denormalize that and say, okay, well, I see that folder A is also attached to document A/B/C, so now there's an edge here. Now there's an edge here from folder 0 to A/B/C. So we need to keep that whole thing denormalized so that we don't have to do an entire graph traversal every single time there's an incoming entry. But the point is that one additional write to Zanzibar may result in thousands or tens of thousands of writes to Leopard, so there can be a lot of expansion as a result of that. Another thing that we do in Zanzibar is going to be caching in order to avoid hotspots. So basically the idea here is that certain ACL objects can be queried very, very often. I think one example that they provide is, let's say there are a bunch of documents that come up in a search index and people are querying that search index constantly. Well, maybe all of those documents are part of a parent folder, and that parent folder is now getting hit on its ACL list every single time that someone queries for any of those documents because, maybe they have permissions from the parent folder. I guess the idea here is that now that's going to become a hotspot because that's just going to be on one spanner node or one spanner shard, and as a result, everyone's going to be querying it a ton. So basically the idea that they try and use to solve this is if we keep this thing in memory, we're going to greatly shield spanner from the number of requests that it may get and be able to return data much faster here. So the way they do that is by using consistent, oh boy. They use consistent hashing on the object ID, meaning that we know deterministically for a given object which server it's going to be cached on. This is going to increase our cache hit rate. And it's also just going to mean that if one of the Zanzibar servers goes down, we don't rebalance a ton of entries. Number 2 is that, okay, we now know where every single object is going to live for its cache, but it's possible that if a new object gets created and then tons of people start querying for it at the same time, we have something known as a cache stampede, where the cache hasn't been filled yet, so all of the requests temporarily go to spanner and then spanner goes down. The way they stop this is using a lock table. So basically, if a bunch of concurrent requests are going through the same caching server to Spanner at the same time, the server is actually going to only allow one of them to go through by virtue of using a lock. Now, what they'll do is basically keep in mind, because we have that parallelism with Boolean trees from before, if one of the expressions that goes to Spanner returns, typically we'll cancel any of the other outgoing ones. That being said, two requests that may need to access the same Spanner table may also need to access the same other pieces of data too. So this time you don't want to cancel any outgoing requests because you want the cache to be warm for those other requests that are stuck in the lock table. So you'll basically check the lock table and you'll only conditionally cancel any outgoing requests that don't need to be made if the lock table is empty and you're not in contention with any other request. Another thing they'll do is cache data at both the caller and the callee level in order to minimize RPC calls between Zanzibar servers, because keep in mind that, because so many of these are like recursive calls via graphs, Zanzibar servers are constantly reaching out to one another. This is ultimately a graph traversal problem, so it's almost like that Facebook Tau design as well. And then finally, for objects that are really, really hot, as opposed to just caching only the return data from Spanner, they'll actually cache the entire set of relationships for that object because it's being accessed so often. And the way they determine that is the server that's responsible for that object will basically just keep track of the outstanding read count for it, and then if it exceeds some threshold, it'll just cache the object in all of its relationships to speed things up. Now, you may think to yourself, okay, well, this is good, but if we're caching all of this data, keep in mind that we need to cache it with some respect to the Zookie timestamp that's used to perform a read, right? Because if I'm interested in the same data as someone else from the ACL list, but we're reading from different snapshot timestamps, then whatever they have cached is not relevant to me. And those timestamps can be, pretty much infinitely discrete because they're timestamps, right? Like they might be at like a nanosecond level, so I'm never going to get any utilization out of caching. What they'll do instead in Zanzibar is they'll basically take every snapshot and execute it at a time that's the timestamp, but rounded up to the nearest second. So you know that you're still getting, reads that are up to date, but at the same time, we've now basically minimized the number of different timestamps that we might use for snapshots, and as a result, we're going to get more utility out of our caching because a lot of reads are going to come in asking for the same timestamp. Cool. The final piece to talk about here is going to be request hedging. So basically, Leopard and Spanner are both services that are actually external to Zanzibar, right? They're not maintained by the Zanzibar team, and as a result, they can have high tail latencies. These are just things that happen when you're dealing with external services. So what they do in order to mitigate this is they'll basically just wait some amount of time when you make a request to either of these systems, and then after that amount of time, they don't get a response, they send a second one. Maybe there was some networking issue, maybe there was a hardware issue. Either way, try again, see if you get lucky. So what they'll do to try and help this out is every single data center that they have a Spanner instance in or a Leopard instance in, they'll just keep two of them in that same data center, the second one being there in the event that you have to send a hedging request. Now it's worth noting that, technically Zanzibar servers are communicating with each other a ton too, right? And some, because they're communicating with each other so much, it's possible that sometimes one Zanzibar server will be waiting a long time for a response from another. That being said, this is pretty normal because these are kind of like highly nested graphs, and so you don't actually want to perform hedging there because that's just going to add more load to the system and slow things down more. They're just doing this for their external services. Alrighty, so in conclusion, having a system like Spanner that's going to not only allow writes to be linearizable but externally consistent is incredibly useful. So this is in contrast to something like Zookeeper, right, where in theory, you could say, oh, why don't we just use Zookeeper for this entire system? It's basically the same thing. We need linearizable writes. We have to evaluate writes, or we have to evaluate reads at local replicas based on a certain timestamp, and you can do that in Zookeeper. But the problem is, in Zookeeper, you're kind of limited to how much you can scale because when you have to scale beyond one cluster, now Zookeeper is using logical timestamps to a log. It's just assigning each write a monotonic timestamp. Just some random number that's getting increased by one every time. And so if we need to make this at Google scale, we would have to do all sorts of weird partitioning and finagling, and we may not be able to do it. Using an external timestamp basically allows us to store these timestamps in any other system, use a bunch of different Spanner clusters, and everything works out really, really nicely. So another thing to note is, Don't be silly and read from the master all the time. Even though you could, and it would be correct, you shouldn't, because then your reads are going to take much longer. We can evaluate the majority of our reads from local replicas just by using the last modification timestamp of the content that we're doing ACL checks for. And then finally, I think 3 important patterns here that you should try and keep with you for your subsequent systems design is going to be basically just caching in general to reduce hotspots. They did this in Tau as well. Obviously, you can still have a ton of requests to one particular cache, but it's just able to handle it much better than a database, which is typically going to be performing reads from disk. Number 2 is going to be request hedging for external systems to help you deal with very long tail latencies. Sometimes things just go wrong, and sending another request can fix them a little bit faster. And then finally, using normalized data while having asynchronous secondary indexes, so basically doing change data capture, allows us to optimize the write path while still be able to serve a lot of reads fairly fast. Anyways, guys, I hope you enjoyed this video. A lot here, but I don't think any of it was overly complicated. So hopefully you got something out of it. Anyways, I'll see you in the next one, and have a great week.